Hello. As you begin your study of logarithms, the most important fact to keep in mind is that a logarithm is an exponent. If you can say that to yourself several times so that you just remember that, you will find it much easier to work problems involving logarithms. Because exponential functions are one-to-one, they pass the horizontal line test, they have inverses. Logarithmic functions are inverses of exponential functions. Here is our definition of a logarithmic function with base b. Recall that for the exponential function, the base b had to be a positive number and it could not equal 1. That's also true for the base of a logarithmic function. We want b to be greater than 0. B cannot equal 1. We say that y is the logarithm of x to base b if and only if x equals b raised to an exponent of y. Notice y is the logarithm of something and y is the exponent that is associated with this base b. Think about the logarithm of x to base b as being the exponent to which b must be raised in order to obtain x. The x here must be a positive number. You cannot take the logarithm of 0 and you cannot take the logarithm of a negative number. So x must be positive, and as we've already said, the base b must also be positive, but b cannot be 1. B must be a positive number different from 1. Here are certain properties of logarithms that come directly from the definition. The logarithm of 1 to base b is going to be 0. Why? Because b raised to an exponent of 0 equals 1. The logarithm of b to base b is going to be 1. Why? Because b raised to an exponent of 1 equals b. The logarithm of b to the x to base b is just x. And b raised to an exponent that is the logarithm of x to base b is also just x. These are inverse properties. The logarithm and the exponentiation are inverse relationships. So if you first raise b to the exponent of x and then take the logarithm of that to base b, taking the exponent and then doing the logarithm, are inverse relationships. You end up with just the x you started with. Or if you take the logarithm of x first to base b and then raise b to that logarithm, again, you're going to just get x. Inverse properties are at work here. Finally, if the logarithm of x to base b equals the logarithm of y to base b, then x must equal y. That's because of the one-to-one property of logarithmic functions. For practice, you should try changing some exponential expressions to equivalent expressions involving a logarithm. We know that 9 is 3 squared. That is equivalent to saying the logarithm of 9 to base 3 equals 2. 2 is the exponent and 3 is the base. If a cubed is equal to 2.1, that's equivalent to saying the logarithm of 2.1 to base a is equal to 3. 3 is the exponent, so 3 is the logarithm, and a is the base. If 3 to the x is 4.6, that's equivalent to saying the logarithm of 4.6 to base 3 is equal to x. X is the exponent, so x is the logarithm here, and 3 is the base. Going in the other direction, if you're given a logarithmic expression, you should be able to change it to an equivalent expression involving an exponent. The logarithm of 1/9 to base 3 is -2. In the equivalent exponential form, that says 1/9 is 3 raised to an exponent of -2. Notice again, the logarithm is -2, so -2 is the exponent that is attached to this base 3. If the logarithm of 4 to base b is 2, 4 is going to equal b squared. And if the logarithm of x to base 5 is 3, then x must equal 5 cubed. You can use the properties of logarithms to understand how to evaluate certain logarithmic expressions without a calculator. For example, the logarithm of 8 to base 8 is 1 because 8 to the first power equals 8. The logarithm of 9 to base 1/3 is -2 because 1/3 raised to the -2 power would be the same thing as 3 to the +2 power, and 3 squared is 9. The logarithm of the cube root of 25 to base 5 is 2/3. Why? Because 5 raised to the power 2/3 is defined to be the cube root of 5 squared, which is the cube root of 25. The logarithmic function with base 10 is called the common logarithmic function and is denoted simply by log without a base written. The unwritten base is assumed to be base 10. The logarithmic function with base e is called the natural logarithmic function, and it's denoted by ln. Some more practice. Without a calculator, use the definition and properties of logarithms to evaluate these expressions. The logarithm of the square root of 3 to the base square root of 3 would be 1, because square root of 3 to the first power equals square root of 3. The logarithm of 3 to the base square root of 3 would be 2, because square root of 3 squared equals 3. The logarithm of 9 to a base square root of 3 would be 4. Why? Because square root of 3 to the 4th power is square root of 3 times square root of 3 times square root of 3 times square root of 3. Square root of 3 times square root of 3 is 3. This square root of 3 times square root of 3 is also 3, and 3 times 3 is 9. So since square root of 3 to the 4th power is 9, the logarithm of 9 to base square root of 3 would be 4. The natural logarithm of 1 over e is -1 because e to the -1 power is 1 over e. 5 times the natural log of e would be 5 times 1, which is just 5. The natural log of 1 divided by 10 is 0. Why? Well, the natural log of 1 is 0 because e to the 0 power is 1, and 0 divided by 10 is 0. And then finally, e raised to the power natural log of 3 is going to be 3 because of the inverse property there again. Here is a graph of a logarithmic function, y equals the logarithm of x to base 2. Let's look at some points on this graph. If x is 1, the logarithm of 1 to base 2 is 0 because 2 to the 0 is 1. So the point 1, 0 is on the red graph, the logarithmic graph. If x were 2, the logarithm of 2 to base 2 is 1 because 2 to the first power is 2. So the point 2, 1 is on the graph. There's 2, 1. If x is 4, the logarithm of 4 to base 2 is 2. 4 is going to equal 2 squared. 2 to the power 2 is 4, so the point 4, 2 is on the graph. If x were 8, and I was taking the logarithm of 8 to base 2, the logarithm of 8 to base 2 is 3 because 2 cubed is 8. So the point 8, 3 is on the graph. What about if x is a fraction getting closer and closer to 0? What happens to y? If x is 1/2, the logarithm of 1/2 to base 2 is -1. Here's the point 1/2, -1. 2 to the -1 power is 1/2. Let's take x smaller. What if x is 1/4? The logarithm of 1/4 to base 2 is -2 because 2 to the -2 is 1/4. If x were 1/8, the logarithm of 1/8 to base 2 is -3 because 2 to the -3 is 1/8. So you can see as x approaches 0, the y value here, the logarithm of x to base 2, is approaching minus infinity. Let's summarize the characteristics of this logarithmic graph that we have just seen. The domain is 0 to infinity. If I'm taking the logarithm of x, x must be greater than 0. The range, as we've seen, is minus infinity to infinity. Our x-intercept is this point 1, 0. The logarithm of 1 to base 2 is 0 because 2 to the 0 equals 1. The graph is increasing as you go from left to right. It's 1 to 1. It passes the horizontal line test, and it's continuous. And as we've seen, the y-axis is a vertical asymptote. As x is approaching 0 from the right, the y value, which is the logarithm of x to our base, which we chose 2, is approaching minus infinity down here. The blue graph is the exponential function, y equals a base to the power x. I chose base 2 again. So the blue graph is y equals 2 to the x. And think about it, you already have learned that if you have two functions that are inverses of each other, the domain of one corresponds to the range of the other, and the range of one corresponds to the domain of the other one. That works here as well for the logarithmic function and the exponential function that are inverses of each other. And if the point 1, 0 is on the graph of the logarithmic function, the point 0, 1 has to be on the inverse function, the exponential function. Also, recall when we studied the exponential graph before, that the x-axis is a horizontal asymptote. As x approaches minus infinity, the y value, which is 2 to the x, is going to be approaching 0. There are several laws of logarithms that will be important for you to know when you're working problems involving logs. One is the change of base formula. If I have the logarithm of x to base a, and I want to change that to a different base, we'll call it base b, the log of x to base a equals the log of x to base b over the log of a to base b. Notice that this expression on the right both involves the numerator and a denominator with log to base b. Why would I want to change from base a to a different base b? Well, that can be particularly useful if I want to change to base 10 for common logarithms or base e for natural logarithms, just because many calculators only have those two types of log keys. Three other properties that are important to know for logarithms are called the product property, the quotient property, and the power property. The product property says the log of a product is the sum of the logs. In other words, the log of u times v is the log of u plus the log of v. We're assuming here that we have the same base throughout for all of these properties. The logarithm of a quotient, u divided by v, is the logarithm of u minus the logarithm of v. It's the logarithm of the numerator minus the logarithm of the denominator. And the power property says the log of this power, u to the exponent of n, is equal to n times the log of u. The exponent here can be brought out front as a factor. We can use these properties of logarithms to sometimes find the exact value of an expression without a calculator. The logarithm of 9 to base 6 plus the logarithm of 4 to base 6. Without a calculator, I have no idea what the logarithm of 9 to base 6 is, and I have no idea what the logarithm of 4 to base 6 is. However, I can use the product property. The sum of these logs is the log of the product. 9 times 4 is 36. And the logarithm of 36 to base 6 is exactly 2 because 6 squared equals 36. If I have the log of 16 to base 8, minus the log of 2 to base 8. I can use the quotient property. That would be the logarithm of 16 divided by 2 to base 8. 16 divided by 2, of course, is 8, and the logarithm of 8 to base 8 is going to be 1. The next problem is a little more complicated. Notice I have the logarithm of 8 to base 3 times the logarithm of 9 to base 2. Here, the bases do not match. All of the properties of logarithms that we have discussed have depended on having the same base throughout. So what I'm going to do here is use the change of base formula to convert everything to common logs. The log of 8 to base 3 is the common log of 8 over the common log of 3. The log of 9 to base 2 is the same thing as the common log of 9 over the common log of 2. Since 8 equals 2 cubed, the log of 8 equals 3 times the log of 2. And since 9 is 3 squared, the log of 9 is 2 times the log of 3. Now notice that the log of 2 in the numerator cancels with log of 2 in the denominator, and log of 3 in the numerator cancels with log of 3 in the denominator. So all I'm left with is 3 times 2, which is equal to 6. In this example, if you look at 5, it's raised to an exponent, which is the sum of 2 logs. The sum of 2 logs is the log of the product. So log of 6 to base 5 plus log of 7 to base 5 is the log of 6 times 7, or 42 to base 5. Now I can use the inverse property. 5 raised to an exponent log of 42 to base 5 is just going to be 42. Two skills that are important when working with logarithms are the ability to expand logarithmic expressions and to condense them. Here we're asked to write each expression as a sum or difference of logarithms and express powers as factors. The logarithm of 25 times x to base 5 would be the sum of the logs, the log of 25 plus the log of x to base 5. And of course, the log of 25 to base 5 is just 2, because 5 squared is 25. So this simplifies to 2 plus the log of x to base 5. The natural log of x divided by e to the x is the natural log of x minus the natural log of e to the x. That's the quotient rule. And the natural log of e to the x is just x. So I have the natural log of x minus x is my answer. Here is another quotient. The log to base 2 of a over b squared would be the log of a minus the log of b squared. And then I can use the power rule to take this exponent of 2 and write it out front as a factor. So I have the log of a to base 2 minus 2 times the log of b to base 2. The last problem just involves several steps. I have the logarithm of a quotient. So it is the logarithm of the numerator minus the logarithm of the denominator. But my numerator, x cubed times square root of x plus 1, is a product. So the log of that product is the sum of the logs, the log of x cubed plus the log of the square root of x plus 1 minus the log of the denominator here, x minus 2 squared. Now I can use the power rule to write these powers as factors in front. So the log of x cubed is 3 times the log of x. Square root sign is the same thing as raising this expression under the square root to the 1/2 power. So I can write this as 1/2 times the log of the expression x plus 1. And then minus, bringing the 2 out as a factor, minus 2 times the logarithm of x minus 2. And I've expanded the expression. Now we want to practice going in the opposite direction by condensing logarithmic expressions. The first thing I do is write this factor of 2 as a power. So twice the log of u is the log of u squared. And the log of u squared minus the log of v would be the log of the quotient, u squared over v. My base here is 3. Here I have the difference of two logs. The first thing I want to do is to write this factor of 2 as an exponent. So this would be the log of x plus 1 squared. And then the difference of the logs is the log of the quotient, the log of x squared plus 3x plus 2 minus this log would be the log of the quotient, x squared plus 3x plus 2 over x plus 1 squared. I can factor this numerator. X squared plus 3x plus 2 is x plus 1 times x plus 2. X plus 1 squared is x plus 1 times x plus 1. The x plus 1 in the numerator cancels with x plus 1 in the denominator, and I'm left with just the log of x plus 2 over x plus 1. Finally, in part C, I have 3 times the log of 3x plus 1 to base 5 minus twice the log of 2x minus 1 minus the log of x. Let's factor a minus sign out of these last two. And so I have a minus sign out front, and then in brackets I would have twice the log of 2x minus 1 plus the log of x. Minus times a plus is a minus. Now I'm going to take the factor of 3 and write it as an exponent using the power rule. And here I'm going to take this factor of 2 and write it as an exponent of 2 using the power rule again. And now within the brackets, the sum of these two logs is the log of the product. And then finally, the difference of these logs is the log of the quotient. So I have log to base 5 of 3x plus 1 cubed in my numerator, and x times 2x minus 1 squared in my denominator. Here is an example of a real-life problem that uses logarithms. If a task is learned at a performance level p sub 0, that's the initial performance at time 0, then after a time interval t, the performance p satisfies the equation the log of p equals the log of the initial performance p sub 0 minus a constant c times the log of t plus 1. C is a constant that depends on the type of task. T is measured in months. We're told to solve the equation for P, the performance, after T months. I can rewrite the right-hand side of this equation as the log of P sub 0 over T plus 1 to an exponent of C. We use the power rule to move this factor of C up as our exponent on t plus 1, and then the difference of the logs is the log of the quotient. Now, by the one-to-one property, this means p has to equal p sub 0 over t plus 1 to the power c. If we're given that c is 2/10 and that our initial performance was a 90 on a history test, what score would you expect to get on a similar test after 2 months? So I just substitute 90 for the initial performance and substitute a 2 for the t. 2 plus 1 is 3. C, we're told, is 2/10. If you enter that expression in your calculator, it comes out to be about 72. So if you made a 90 on the test initially, after 2 months, you might only score about a 72 because you would have presumably forgotten a good bit of the material in that 2-month time period. That's just one example. There are many, many applications of logarithms. Hopefully you will enjoy studying this topic and working with expressions involving logarithms, and then you will learn to solve equations with logarithms in them.